our previous build, agent number 3, the Memory-Augmented agent, solved a critical continuity problem. By mapping interaction logs into a vector space, it gave the system the ability to recall past context, allowing a conversation to span days or weeks. But memory alone is incomplete. This brings us to agent number 4, the Knowledge Retrieval Agent. As we advance into the knowledge and retrieval tier, the system moves past tracking stateful memory and into executing grounded data retrieval. This architecture opens Chapter 6 of the book 30 Agents Every AI Engineer Must Build by Imran Ahmad. The Memory-Augmented agent has a structural limitation. While it remembers the specific user conversation perfectly, its general world knowledge ends at its training cutoff date, making it blind to current enterprise data. If you ask a bare language model for last quarter's revenue numbers or a compliance law passed last Tuesday, it will generate a response that possesses the fluent, confident shape of a true answer, even when the facts are entirely fabricated. Mark Twain captured this danger perfectly. He wrote that the difference between the almost right word and the right word is the difference between a lightning bug and actual lightning. A bare model gives you the lightning bug, a plausible hallucination lacking real power. To get the lightning, we need a sharp, externally retrieved fact. A plausible but wrong answer is the most destructive failure mode in a production environment. Solving it requires an agent that operates on a strict new rule. It must refuse to answer from its own internal memory. Instead of answering from what its weights remember, this agent's prime directive is to go fetch the actual lightning from an external source and prove exactly where it came from. This diagram outlines the 5-stage grounded retrieval pipeline. It maps the flow from a natural language query down to a verifiable output. It begins at stage 1, query understanding. The agent intercepts the user's input, parses the true intent behind messy phrasing, and decomposes multi-part questions into targeted search parameters. Next is stage 2, the retriever module. Here, the agent executes lexical, semantic, or hybrid searches across external knowledge stores, like vector databases, to pull the raw data chunks that match the query. Stage 3 is pre-processing. Retrieving a dozen raw hits isn't enough. The agent re-ranks those hits, filtering the noise so only the highest density evidence rises to the top of the context window. In stage 4, reason and generate, the core language model thoughtfully speaks, but it is now mathematically constrained. Its prompt explicitly instructs it to compose its answer using only the retrieved, re-ranked context. Forcing the reasoning engine through these sequential gates anchors the generation phase to the retrieved evidence, preventing the model from relying on its internal, frozen weights. But there is a final layer to this architecture. Running parallel to the entire pipeline is stage 5, provenance. The provenance layer tracks citations, source metadata, and confidence scores through every transformation of the data payload, operating concurrently with the main retrieval path. That thread physically ties the generated output back to its origin. As the model synthesizes the answer, it staples a specific citation bracket to the end of every generated claim. The inclusion of this continuous provenance thread is the architectural difference between a chatbot providing a guess and an enterprise agent providing a verifiable audit trail. This block diagram proves the shape of the idea on paper. It outlines a stable, complex, and complete retrieval system. But a diagram only proves the theory. To truly understand how this agent reformulates a query, re-ranks passages, and cites its claims, we have to move past the blueprint and watch it run in real Python code. This code block from Chapter 6, the first step is ingestion. The DirectoryLoader targets a local folder, pulling in raw text, PDFs, or HTML files to serve as the agent's external library. We then pass those files through a RecursiveCharacterTextSplitter. We set the chunk size to exactly 1,000 characters to prevent the model from drowning in irrelevant context during a search. We also configure a 200-character overlap. If a crucial sentence spans the boundary between two chunks, this overlap ensures the semantic context survives the cut. Text alone isn't searchable by meaning. We have to translate those chunks into mathematics. This second block of code converts the text into dense embedding vectors and indexes them inside a local FAISS database. We then wire that database directly into the language model using a RetrievalQA chain. Pay close attention to this specific parameter. Return source documents equals true. This single line activates the provenance layer. These specific lines enforce the agent's prime directive. It is explicitly forbidden from guessing based on its internal weights. If it makes a claim, it must staple a verifiable receipt to it. To see how the Knowledge Retrieval Agent solves this, watch what happens when an employee asks a corporate assistant, "What's our parental leave policy?" The agent projects that query into a mathematical coordinate space. It bypasses rigid keyword matching entirely. Instead, it snaps to a cluster of nodes containing a document titled "Time Off for a New Baby." It retrieves the document because the underlying semantic meaning matches the intent. When the agent generates the final response, a provenance ribbon threads through the logic, explicitly linking the output sentence back to Section 4 of the official HR document. This exact tracing mechanism scales. It processes recent case law for legal summarization and cross-references analyst reports for fast-moving market intelligence. You cannot deploy AI in a regulated enterprise on blind faith. A visible, mathematical traceback to an unaltered source document is the only way to establish trust. But this architecture is not bulletproof. If you misconfigure the retrieval rules, you create entirely new categories of failure. Imagine a user asks for the company's subscription refund policy, but that specific document was never ingested into the agent's index. Instead of admitting ignorance, a naive retriever scrambles. It pulls the mathematical next closest match, grabbing a file for general billing terms. The model reads those generic terms and generates a highly specific, fabricated answer about refunds, complete with a citation linking back to the irrelevant billing document. This is significantly worse than a standard hallucination. The presence of a clickable citation creates a dangerous costume of authority for a fabricated fact. To prevent this, we enforce strict deployment rules. First, never use a retrieval agent for pure reasoning, mathematics, or creative writing. If there is no fact to fetch, the pipeline only adds latency and noise. Second, never deploy on a stale corpus or one lacking strict user-level access controls. An unpermissioned agent will happily retrieve and cite your CEO's payroll data. Finally, if the user's vocabulary relies on acronyms or specific product codes that don't match the embedded corpus, pure semantic similarity will fail. You must implement a hybrid search that incorporates BM25 keyword matching. Implementing retrieval without comprehensive coverage, strict vocabulary alignment, and tight latency budgets does not cure hallucinations, it weaponizes them. This map shows Agent 4's place in the 30-part progression. Agents 1 through 3 establish the foundational cognitive tier, decisions, planning, and memory. Agent 4 opens the knowledge and retrieval tier, the required architectural layer making those cognitive functions grounded, factual, and auditable. But this entire system relies on a massive underlying assumption that the corporate data feeding the vector database is perfectly clean, formatted text. The physical reality of enterprise data is a chaotic mess. It's filled with faded receipts, nested tables, and scanned PDFs that standard splitters cannot parse. Before we can search and retrieve data, we have to extract it. We need a specialized system capable of optical character recognition, layout parsing, and rigid schema extraction, which leads us directly to our next build, Agent 5, the Document Intelligence Agent. To see the complete code for today's RAG pipeline, pick up a copy of 30 Agents Every AI Engineer Must Build by Imran Ahmad. Subscribe to the NeuralCA channel and join us in the next episode as we extract structured, citable intelligence from a messy physical world.